In this video, we're going to look at other types of equations such as solving rational equations, use rational functions, and solve rational equations for a specific variable. So if I were asking you all to find the domain of this first question, g of x is equal to 1 over 3 minus x, we know at this point what we're going to do is take the denominator and the value underneath the square root. We're going to say that this has to be strictly greater than or equal to 0 if it wasn't in the denominator. Because it's in the denominator, we're going to go ahead and it has to be strictly greater than. Because if it's equal to 0, I'd be dividing by 0. So now I would go ahead and add x to both sides, and I say that 3 is greater than x. Or I could say that x must be less than 3. In interval notation, this would be from negative infinity to 3 with a parenthesis, and set builder notation x such that x is less than 3. Either one of those is sufficient. If I were to look at part B, h of x, we know from our last video that this is where the vertical asymptotes would happen. And we say the denominator x plus 5 cannot equal 0. So we know that x cannot equal negative 5. Interval notation would be from negative infinity to negative 5, union between negative 5 to infinity. And if I was doing set builder notation, x such that x cannot equal negative 5. If I were, and this should be number 2, if I were asked to add these fractions together, I would first need to find the lowest common denominator, because once my denominators are the same, I can add the numerators. And my lowest common denominator between 2, 5, and 10 is 10. It is not necessarily going to be 2 multiplied by 5 multiplied by 10. It is the lowest common multiple they all share, which happens to be 10. So now I need to multiply each one of these fractions here, 1/2 to 3/5, by whatever number, numerator and denominator. That gives me a denominator of 10. In the first instance, I'm going to multiply by 5 over 5. And in the second fraction, I'm going to multiply by 2 over 2. Then I'm going to get 5 over 10 plus 6 over 10 plus 7 over 10. Now that they have a common denominator, I can write this all over the single common denominator, 5 plus 6 plus 7 all over 10. And we know that 5 plus 6 is 11, plus 7 more is 18 over 10. And of course, this does reduce by a factor of 2, so I get 9 over 5. And that is my final answer. If I look at part B, I'm going to do this similar to what I just did in part A. The difference between part A and part B is that part A has strictly numeric denominators. In part B, we have denominators that are going to include, the lowest common denominator is going to include a 4, that comes from here, and then the x squared, and that's the highest power on that variable. So again, what I'm going to do is multiply by what's missing in the denominator to make each denominator become 4x squared. So this first fraction needs to be multiplied by both a 4 and an x. And the second fraction, I'm just going to erase this. The second fraction needs to be multiplied by an x squared, numerator and denominator. And then my third fraction needs to be multiplied by a 4, numerator and denominator. So I'm going to get 8x over 4x squared plus 3x squared over 4x squared, and then minus 28 over 4x squared. Now that they all have a same common denominator, I can put them all over that same common denominator. So I get 8x plus 3x squared minus 28 all over 4x squared. Now I can see that I have no common values in the numerator that I could factor out to cancel with the denominator. So the best I'm going to do is just rewrite it in descending order. So I have 3x squared plus 8x minus 28 all over 4x squared, and that is good as that gets. So if I have a rational equation that is basically an equation that involves rational expressions, the first thing I'm going to do actually is find the lowest common denominator, just like I did up above on those fractions. The second thing I'm going to do is state my restrictions. Of the denominator based on the lowest common denominator. The third thing I'm going to do is multiply each fraction by the LCD. And what that does is, unlike up above where I was simplifying into a single fraction, now I am solving, which means I can multiply both sides by that same lowest common denominator, which will clear my fractions. So I'm going to multiply each fraction by the lowest common denominator to clear the fractions. And then I'm going to just solve. Now this equation should not have any fractions. And then the last and final thing is I should check solutions, and I should check the solutions against the restrictions. Okay, so on the very first example here, first thing I'm going to do is write down my LCD. My lowest common denominator will be a 6, because that's the lowest multiple between 3 and 6 that they both share, and an x, and that comes from here. Right now I'm going to say x cannot equal 0, just in case I come up with a 0. Unlikely, but it could. So in case I get into 0, then I would take and say that if I get x is equal to 0 when I solve, that would tell me that x is equal to 0 is an extraneous solution. Now, I'm going to clear fractions. I am not trying to make a single fraction on one side and a single fraction on the other. Instead, unlike up above, I'm going to clear fractions, and I'm allowed to do this because this is an equation. So I'm going to multiply each term by the lowest common denominator over 1. Every single term will get multiplied by the lowest common denominator over 1. What this does is it clears your fractions. So this will cancel down to 2x minus the 6's cancel, leaving me minus 5x. And then here my x's cancel. And I wrote x, even though I just said it canceled, so it would be a 6. So I'm going to get negative 4x is equal to 6. X is equal to negative 6 over 4, which reduces to negative 3 over 2. Now I should check this, so let's go back and put it in the original function, which is 1/3 minus 5 over 6 is equal to 1 over x. So 1 over negative 3/2. Checking to see if this works. So on the left-hand side, unlike before, since I am checking it, I'm going to multiply this by 2, numerator and denominator. So I end up with 2 over 6 minus 5 over 6. Now on the right-hand side, I'm going to have a fraction, which is 1 over 1. So I have really 1 over 1 divided by negative 3 over 2. So when I have a fraction divided by a fraction, it is the multiplication of the numerator fraction and the reciprocal of the denominator fraction, so it's going to be negative 2/3. And then on the other side of the equation, I'm going to have 2 minus 5, which is 4, negative 4 over 6, negative 2/3. And yes, that does indeed check. Similarly on B, my lowest common denominator is going to be this, which is 3x plus 2 multiplied by this. So I have 2x multiplied by 3x plus 2. I'm going to state my restrictions. X cannot equal 0 from this one, and x cannot equal negative 2/3 from this one. I'm going to multiply this side by the lowest common denominator, which is 2x multiplied by 3x plus 2, and over 1. I'm going to multiply this side by that 3x plus 2 multiplied by that 2x over 1. The left-hand side, the 3x plus 2 cancels, leaving me 5 multiplied by that 2x. On the right-hand side, the 2x's cancel, leaving me 3 multiplied by 3x plus 2. On the left-hand side, I'm going to get 10x. On the right-hand side, I'm going to get 9x plus 6. I'm going to bring the 9x to the left-hand side, and so I get x is equal to 6. So this is not a restriction, so that's good. Now I'm just going to check it by putting it in here. So I'm going to have 5 over 3 multiplied by 6 plus 2. Does that equal 3 divided by 2 multiplied by 6? On the left-hand side, I have 5 over, I have 18. 3 times 6 is 18 plus 2, which is 20. And on the right-hand side, I get 3 over, I'm checking to see if this is true, 3 over 12. Well, the left-hand side reduces to 1/4. The right-hand side reduces to 1/4, so this does check. If we take a look at part C, we're going to find our lowest common denominator. But in this case, I'm going to have to factor first before I find my lowest common denominator because this is not completely factored. So I'm going to go ahead and rewrite this as 3 over m plus 2 plus 2 over m, that's a phenomenal m, is equal to 4m minus 4 all over m minus 2, m plus 2. Now, my lowest common denominator is going to be this m multiplied by the m minus 2 multiplied by the m plus 2. That comes from the m minus 2 comes from here, and then the m plus 2 comes from here and here. So that's my lowest common denominator. This tells me that m cannot be 0, it can't be positive or negative 2. So now I'm going to come back and I'm going to multiply by my lowest common denominator over 1. To make my life easier, I'm just going to write LCD over 1 and LCD over 1. And rather than have a string of multiplications, this should be an arrow. So this is an arrow, not a string of multiplications. So when I multiply my LCD over 1 by the fraction 3 over m plus 2, the m plus 2's cancel, leaving me a 3 left standing and an m minus 2 left standing. On the next term, I'm going to have 2 over m multiplied by my LCD. In this case, my m will cancel, leaving me both a 2 in the numerator and then the m plus 2 and then the m minus 2. On the right-hand side, when I multiply this by my lowest common denominator, the m minus 2 and the m plus 2 both cancel because that's where it came from, was here, leaving me an m multiplied by 4m minus 4. Left-hand side, I'm going to go ahead and multiply through, and so I'm going to get 3m squared minus 6m. I'm going to distribute these two onto here and onto that term, so both terms. And then I'm going to have plus, I'm going to get 2m squared minus 8. Because I know that m plus 2 and m minus 2 really is m squared minus 4, so I distribute the 2 on that, which gives me 2m squared minus 8. Equals 2, and then on the other side of the equal sign, I'm going to get 4m squared minus 4m. Now I'm going to bring everything to the left-hand side. I have a 3m squared, I have a 2m squared, that gives me 5m squared, but then I'm going to subtract off a 4m squared, so I'm going to be left with m squared. That's 3 plus 2 minus 4, because the minus is on the right-hand side of the equal sign. Then I have a negative 6m. This is a negative to begin with, but I'm going to add it to both sides, so I'm going to have a negative 6m plus 4m, which gives me negative 2m. And then the only thing left standing is that negative 8. This is equal to 0. This is a quadratic, so I'm going to treat it as such. Two factors of 8 that have a difference of 2, which is 4 and 2. So m minus 4 and m plus 2 is equal to 0. So I end up with m is equal to 4 and negative 2. Notice that this is one of the restrictions. So even though algebraically I came up with a solution, this is actually extraneous. is an extraneous solution. And so I'm going to let you check the 4, and I want you to know that if you would have checked the 2, the negative 2, you would have actually found right here would have produced a 0, and over on this one would also have produced a 0 in the denominator. So you would have found that by the checking as well. And I believe this is almost my last one for these types. So again, what I'm going to go ahead and do is factor. This is x minus 1 and x plus 1. So my lowest common denominator happens to be x minus 1, x plus 1. That tells me that x cannot equal negative or positive 1. Multiplying each one of these by the LCD, it's terrible LCD over 1. And this is the LCD over 1, and this is the LCD over 1. When I multiply the LCD over 1 by this term, the x minus 1 cancels, leaving me an x that is currently there, and then the x plus 1 that's still standing, minus. Similarly, here the x plus 1 will cancel. I have a 1 left over, and the x minus 1. So I have minus 1, x minus 1. And on the other side of the equal sign, both the x minus 1 and x plus 1 cancel out, so I just get 2. So I end up with x squared plus x minus x plus 1 is equal to 2. So I'm going to get x squared. These two give me 0. I have a plus 1 minus 2 gives me a minus 1, which is equal to 0. I end up with x is equal to positive and negative 1. However, they're both the restrictions, so this is a no solution because both positive 1 and negative 1 were extraneous. If I'm asked to solve a rational equation for a specific variable, I'm going to follow the same process as before. I'm still going to find my lowest common denominator, and then I'm going to solve. So my LCD, in this case, this is 2 over 1, is s multiplied by t multiplied by 1. So I'll multiply this by the LCD over 1, this by the LCD over 1, and this by the LCD over 1. Now when I multiply the first term by my LCD over 1, my s's cancel, leaving me 3t. Plus, and when I multiply my second term on the left-hand side by my LCD, my t's cancel, leaving me just s. And then on the right-hand side, I end up with both s and t, so I have 2s t. Now any t or any s, which I'm solving for here and here, need to go on one side of the equal sign and everything else needs to go on the other. I'm going to choose to subtract s from both sides, so I'm going to have 3t is equal to 2st minus s. I'm going to factor an s out of these two terms so I can isolate it. So I have 3t is equal to s, 2t minus 1. Now I'm going to divide both sides by the 2t minus 1 because that way I can isolate for my s. So I have 3t over 2t minus 1 is equal to s, and I have solved for that particular variable. The final example here, that I'm going to have you ponder this question, is to solve for n. My LCD, this is over 1, is just 2 minus n. Okay, so I'm going to multiply this by the LCD over 1 and this side by the LCD over 1. On the left-hand side, nothing cancels, so I'm going to end up with m, 2 minus n. On the right-hand side, I get n. So I have 2m minus nm is equal to n. Again, I'm going to move the n and the nm, this term, to the right-hand side. So I have 2m is equal to n plus nm. On the right-hand side, I'm going to factor out an n so I can isolate it. So 2m is equal to n, 1 plus m. Divide both sides by 1 plus m. I'm going to have 2m is equal to 1 plus m. 2m divided by 1 plus m is equal to n, and there is my final solution. And this, why is it important to state the domain restrictions on a rational equation? Take a look at why I did that on the last couple of examples when I was solving the equations and not for a specific variable, and that should answer your question. And that's it for this one.